Okay, let's do an example where we're actually going to use our elementary row operations to solve a system. So let's say we have this system here, um, and we want to solve it for the values of x1 and x2 and x3 that make this system true. First thing, it's given us sort of as a system of equations. We're going to want to turn this into augmented form. Which is matrix form with the right-hand side sort of glued in there as well. And so I'm going to essentially extract all the coefficients from my left side, and they're going to be the entries in the matrix part, and then I'm going to have a vertical bar, and then I'm going to have my right-hand side. Okay, I can label the columns here with x1, x2, x3 for that then will represent the coefficients. So one thing to be aware of is there's no coefficient x or no variable x1 in this first equation. We can think of that as 0 times x1 plus that. Okay, so if there's nothing, if that variable doesn't show up, then you can think of it as being 0 times that. And so this first row is 0 x1s, 2 x2s, 1 x3, and that's going to be equal to 6. And I often label my right-hand side as B. My second row is going to be 1x1, 1x2 minus 1x3, and that should be equal to 2. And my last row is going to be 2, 1, 1, and that should be equal to 4. So I took my system, I turned it into matrix form, but specifically augmented matrix form, where we glue the right-hand side onto the end of the matrix. Because we'll include that right-hand side in our row operations. And by doing that, we essentially follow the fundamental rule of math, which is do unto both sides of the equation the same thing. So let's talk a little bit of strategy. There's a couple equivalent ways of going about this. Essentially, we want to get a bunch of zeros in here by using our row operations. I like to follow the strategy of trying to get it so that there are zeros below the diagonal. So I want to turn this, and this into zeros. Okay, and then we can use back substitution. You could take it further than that and get a bunch more zeros so that you only have one non-zero in each row, and that'd be great. But usually that's as far as I need to or want to go. So strategy is I'm going to want to get 0, 0, 0 here below this sort of diagonal line. Okay, first thing I'll notice is I've got 1, 0 already. And so let's make use of that. And I'm allowed to swap my rows. So I'm going to go ahead and swap the first 2 rows to bring that 0 into one of the spots where I'd like a 0. So first step is I'm going to take row 1 and row 2, and I'm going to swap them. So that will bring the row 2 up to row 1. So 1, 1, negative 1, 2, and bring row 2 down to the second spot. Row 3 will stay the same. Okay, so I've got 1, 0 here. I want to turn this into a 0 and this into a 0. Let's start with how can I turn this into a 0? And I look, if I want to operate on it, and when I want to add one of the rows down, this 0, if I were to take row 2 down to it, wouldn't do anything to it because zeros don't do anything. Instead, what I'll do is I'll use this 1 up here, and I want to take a copy of row 1 or a multiple of row 1 and add it to row 3 in such a way that this 2 gets zeroed out. So what do I need to do? Well, I'll take negative 2 row 1 plus row 3 and put that into row 3. The goal is that I want to turn this into a 0. If I take negative 2 times 1 plus 2, that will turn that into a 0. So I kind of smartly choose what multiples of which rows I use in order to get a 0 where I want to get a 0. So row 2 is going to stay the same. So if you wanted to write out row 2, row 1 will stay the same. So let's go ahead and just copy those 2 rows down. Now I'm going to take -2 times this row, add it down to this. So -2 times 1 plus 2 gives us 0. -2 times 1 plus 1 is going to give us -1. And -2 times -1 is +2 plus 1. That will give us 3 there. -2 times 2 plus 4, that nicely gives us a 0 there. Okay, so now I've got 2 of the spots that I wanted 0 are 0. Now let's work on getting this one turned to 0. The trick is once I've turned both of these to 0, I now don't want to use row 1 anymore, because if I were to add row 1 down to row 2 or row 3, that would fill in these zeros, and I want to avoid filling them in because I want to keep them as zeros. So now I'm just going to be using rows 2 and 3 to try to cancel this out. Okay. I've found the easiest way to do this is I like to do it sort of in 2 steps. I'm going to turn this into a 1 here, and then I'm going to add down to there to cancel that out. I could do it in 1 step, but I'll do it in 2 steps just to kind of show you. So I'm going to take 1/2 times row 2 and put that into row 2. And so that's going to turn row 2 into 0, because 0 times 1/2 is 0. 2 times 1/2 is 1. 1 times 1/2 is 1/2. And 6 times 1/2 is 3. And I'm going to leave the other 2 rows alone. Okay, now in order to get a 0 here, I just need to add these 2 rows together. And so row 2 plus row 3, and I'll put that into row 3. And that will give us 0 plus 0 is 0. 1 plus -1 is 0. 1/2 plus 3 is 3.5 or 7/2. And 3 plus 0 is 3. Okay, I didn't change rows 1 or 2, so I'll go ahead and copy those down. Okay. So I'm going to stop with the row operations at this point. The reason why is from this point, I've got my system into a format where I can really go ahead and solve from here. So the key thing is that if we remember what our row operations do is they transform our original system into another system that's equivalent, meaning that it has the same solutions. So really, if I remember that this first column represents coefficients of x1, the second column represents coefficients of x2, and the third column represents coefficients of x3, I can read off this last row here as 0x1 plus 0x2 plus 7/2 x3 equals 3. And notice there's no x1 and x2 in this equation, so it's pretty easy to solve for x3. Namely, I'll multiply both sides by 2/7, and that will tell me that x3 equals 2/7 times 3, which would be 6/7. Okay, so I solved for x3. Now I'm going to start doing what's called back substitution. So now I work my way back up, and I look at this next equation. Notice that this next equation doesn't have any x1, it only has x2 and x3. So it's 0x1 plus x2 plus 1/2. Now I know the value of x3, and so I'm actually going to plug that in as 6/7 equals, my right-hand side isn't 3. Okay. Now I just want to solve for x2. 1/2 times 6/7 will give us 3/7, and then I'm going to go ahead and subtract that over the other side. And that will tell me that x2 is equal to 3 minus 3/7. Let's see, yeah, 3 is 21/7 minus 3/7. That will give us 18/7. Okay, finally, if I look at this row, now this has all of them, but I've got x1 plus x2. I can fill in 18/7 minus x3, which is the 6/7, equals 2. Okay, and let's maybe bring this down here. So x1, 18/7 minus 6/7 will give us 12/7 equals 2. I'm going to subtract this 12/7 over the other side. 2 is 14/7. So that gives us x1 equals 2/7. So now we've found x1, x2, and x3. Turns out these are the only solutions to this system. And so our vector x is the vector. Now we just got to make sure we put them in the right order. So x1 first, x2 second, and x3 third. And that's our final solution.